This is Organic Chemistry Topic 10, Video 1. Organic chemistry is a study of biological molecules. So all fossil fuels, synthetic materials such as the stockings and nylon materials, and many industrial products are made up of organic molecules. The key ingredient to being an organic molecule, and what organic chemistry is all about, is this special element, carbon. And carbon is so unique or special because it has the ability to bond to itself and forms long chains as well as rings. If a compound does not contain a carbon atom, they're called inorganic. So when you get to college, if you study chemistry and you're studying organic chemistry, it's going to involve the properties of carbon and reactions with carbon. If you're taking inorganic chemistry, that means that you are taking chemistry that is not involving carbon-based compounds. The simplest type of organic compounds are called hydrocarbons. We need to know the definition of a hydrocarbon as containing only carbon and hydrogen atoms. So if something is CHO in the formula, it can't be a hydrocarbon because it contains an oxygen. So strictly hydrogen and carbon only. Here are some examples of hydrocarbons. We have methane, which is CH4. It's natural gas. We use methane to heat our homes. Propane is used as a heating fuel. Hydrocarbon chains that have 5 to 12 carbon atoms are typically found in gasoline and petroleum. And then carbon chains of 20 or more are those that are typically going to be found in candles and wax. And think about the fact that if you have 20 or more carbon atoms, you're going to be very nonpolar. So that's the kind of materials that we typically see in candles and wax, as well as petroleum oil and gasoline, very nonpolar molecules. We need to know all the homologous series just as we did in Regents chemistry. So you have an alkane, means that something is going to be single bonded. The general formula for an alkane is CnH2n plus 2. An alkane is going to end in ane. So when you're single, you end in ane and you have a single bond, and that means you're a saturated hydrocarbon. Unsaturated hydrocarbons are those that have double or triple bonds. So single begins with S, those are saturated. Unsaturated have double and triple. So alkenes and alkynes are unsaturated. Alkenes, those compounds that end in ene, have a double bond, whereas alkynes, compounds that have a triple bond, are going to end in yne. The general formula for an alkene is CnH2n, which basically means however many carbons you have double the amount of hydrogen. So it's C3H6, C4H8, C5H10. Alkynes have double the amount and then subtract 2. So let's say you're C5H10, then you would subtract 2, so it would be C5H8. And for an alkane, it's double, so C5H10, and then you add 2, so it would be C5H12. When naming hydrocarbons, you're going to name the prefix first, and then the suffix. The prefix is just going to be how many carbons there are in the chain, so meth, eth, pro, bute, pent, hex. These are numbers that we should be familiar with just from learning last year in Regents chemistry. And then we need to be able to apply the appropriate ending. So ane for a single bond, ene for a double bond, yne, or ine for a triple bond. There are different types of formulas, and we've already talked about a few this year, but let's just recap. We have molecular formulas. Those are the non-reduced version of the compound, so C2H6, as opposed to the empirical form, which is the most reduced version of the compound, so CH3. We also have structural formulas. Those are the graphic or displayed version. So if you look at this picture, this is a structure showing you what this compound looks like. It could also be called graphic or the displayed formula. You must include all the H's. If I don't have the H's, so if it's just left blank, that's called a skeletal structure. So a little different than Regents chemistry where you could do it either way. Here the structural will have all the hydrogens, skeletal has no hydrogens. And then you have the condensed structure, which is just showing you the arrangement of the atoms. So here it's C is connected to 3 H's, so you would say CH3, then there's a C with 3 H's. So CH3, CH3. Here we have a stereochemical formula. You may have seen pictures of these types of formulas, but we have not discussed them yet this year. So this is a formula that shows you the actual arrangement of the atoms and bonds in three-dimensional space. So here's our carbon atom. We have the hydrogen atoms are in the plane. This dashed line, it kind of looks like a bolded line, would be the atom coming out at you. So it would be coming out of the page towards you. And the hydrogen that's dotted here, the dotted line means that it's going behind the page. So this H would be coming out of the page towards me, and the other H would be going back behind the page. So here are some examples of alkanes. We have CH4, C2H6, C3H8, C4H10. If you notice, as you add a carbon, the number of hydrogens goes up by 2. So carbon goes up by 1, 2 to 3. Hydrogens goes up by 2, 6 to 8. Carbon goes up by 1. hydrogens going up by 2. So every member of this alkane series differs by a CH2. And that's what defines a homologous series. So every additional member will go up by a carbon and 2 hydrogens. All these compounds have similar chemical properties. And basically what's just happening is that as you increase, since you're increasing the number of carbons, you're increasing the molecular mass. So remember, that means that the boiling point will increase. Your London dispersion force is increasing because the molecular mass is increasing, which would mean that the boiling point increases as we go down, or increase the number of carbons. Homologous series are not just unique to alkanes. You could have homologous series in alcohol. So we have CH3OH, C2H5, so an addition of a carbon, 2 hydrogens. Moving on here, we have addition of a carbon, 2 hydrogens. So each member has an additional carbon and 2 hydrogens, an additional CH2. The members of this series have similar physical properties, but there's a graduation in the physical properties, meaning that the boiling point and intermolecular forces increase, and that's due to the increasing molecular mass and London dispersion forces. Here are some examples of alkenes. Remember, ENE means that you're a double bond. The general formula is CnH2n. So if I have 2 carbons, I have double the hydrogens. 3 carbons, 6 hydrogens. 4 carbons, 8 hydrogens. So this would be ethene, because 2 carbons is eth. The ending is ENE. This is 3 carbons, so prop, ending ENE. 4 carbons, bute, ending ENE. Because remember, we have to memorize the prefix number, so meth being 1 carbon, eth being 2 carbon, prop, bute, pent, hex, etc. We want to be able to draw alkane structures as far as the structural formula and the condensed structural formula. So what I'd like you to do is pause the video and try to draw what these molecules would look like. Okay, so here's CH4, so that's a carbon with 4 hydrogens. Again, you have to draw the H's. Here we have CH3, CH3, so you have CH3, CH3. That's C2H6 in general. Then we had C3, H1, 2, 3, 4, 5, 6, 7, 8. If you look here, our condensed structural form would be CH3. This is CH2, CH3. And then lastly, we have a 4-carbon alkane, so C4H10. So you have CH3, C with 2 H's, next comes C with 2 H's, and then C with 3 H's. In addition to forming chains, carbon can also form rings. An aromatic compound is a carbon-containing compound that's a cyclic structure. The most common example that we're going to be talking about in this unit is a benzene ring. A benzene ring consists of 6 carbons as a hexagon, as you see here, with alternating single and double bonds. So if you look at the structure, where there's additional line represents a double bond. So single bond, double bond, single bond, double bond, single bond, double bond. Each point on the hexagon represents a carbon atom with an H atom attached to it. Benzene may also be represented as a 6-figured hexagon with a circle in the middle. And this circle represents the fact that there is resonance within the structure, because this double bond could be moving here, this double bond can move here, and this double bond can move here. So it doesn't necessarily have to be this way on these 3 particular sides of the hexagon. They could be on the opposite 3 sides. So there is resonance in the benzene molecule. The benzene molecule is planar, and it is symmetrical. The delocalization of the electron clouds makes the molecule stable. The hydrogen atoms on the benzene can be substituted by different groups. So for example, you could have a chlorine or a halogen attached to it. For example, the TNT, which is common military explosive, I'm sure you've heard of it, contains a benzene ring with a methyl group, a CH3 group attached to it, and 2 NO2 groups branching off the ring. So looking at the following structures, this is an alkane, all single bonds between the carbons. This is an alkene because it has a double bond between its carbons. This is an alkyne because it has a triple bond between the carbons. And this is an aromatic because it's a cyclic hydrocarbon. Lastly, we need to talk about some properties of hydrocarbons. First of all organic compounds are going to be containing carbon, covalent bonds, because carbon to carbon is a nonmetal to nonmetal, so covalent bonds, which means electrons are going to be shared. The covalent compounds are not going to dissociate into ions in solution, as covalent compounds do not do this. They do not dissociate into ions, therefore they're poor conductors, there's non-electrolytes. Therefore, the type of van der Waal attraction between them would be London dispersion. So I wouldn't write van der Waals, because actually we talked about how IB changed it to London dispersion. So the attraction between molecules would be London dispersion. And lastly, as was mentioned earlier, as you increase the number of carbons, you increase the London dispersion forces, which means that the boiling point will increase. So if we look at methane, starting at negative 164 all the way up to hexane at 69, we see that the boiling point goes up. Methane, ethane, propane, butane are gases at room temperature. As we increase the strength of the intermolecular forces, we see that we become a liquid. So remember, solids have the strongest intermolecular forces. So the boiling point increases as the molecular mass increases. Those are due to the London dispersion type of van der Waals forces. So increasing boiling point due to increasing London dispersion. Additionally, as you add more carbon atoms, their density and viscosity will also increase. So this last piece of information is new information. Increasing carbons increases the density and viscosity of the compound.